In this video, we're going to take a look at a couple of things with regards to how we actually calculate the magnetic field coming from a current. Now, this technique is sort of the most generalized technique, the Biot relationship. We're going to look at the specifics for a long straight wire, which is a formula that's on your equation sheet that you can just use. But we also want to look at kind of how would you actually derive this if you had to. I know half of my face is in shadow and half of it is in light. It's a very nice sunny day out there, and this is the inside of the room. So that's what we're going to look at. I will say you do not really need to be able to recreate most of this. We'll highlight the things that are really important as we go. We talked about the right-hand rule, which is the directional piece of this that basically says if your thumb is the direction of the current in a current-carrying wire, this is conventional current, then your fingers wrap around that wire of your right hand and show you the curling magnetic field. So if we know how to do that, we can sort of surmise that it would probably become weaker the further away you get, and we want to kind of formalize all those pieces. So we're going to dive into some units here. The unit for the magnetic field is the Tesla, named for Nikola Tesla, and we'll talk about the exact units of it, but it's a Newton per amp meter, and when we talk about magnetic force, that will become, I think, more obvious. But in the meantime, we're still going to be using Tesla. When it comes to calculating the magnetic field, the different arrangements, we don't have an equivalent for Coulomb's law here because there's no such thing as a magnetic monopole. You can't have just one positive or negative, north or south pole. Unlike with electricity, you can have a positive or negative charge. But just like the integration form of Coulomb's law, we have Biot, and that's what we're going to be looking at today. The basic idea is that if you take a little bit of current, a dI, and you kind of figure out the effect of the magnetic field, dB, the little tiny bit of field at some point P due to that current, then you could add up the effect of a bunch of different bits of current. So there's an arbitrary point P. We're going to sum up the effect of that little bit of current, which we know from the right-hand rule is out of the page. And so that's going to be current times dL, the little bit of length that we're dealing with there. And that's the important piece. It's just like we've done before with these kind of integrations. We can't integrate with respect to current. We end up integrating with respect to a position variable. So what do we think affects this? It turns out it's proportional to current, and it's proportional to 1 over r squared, which is, again, probably not that surprising. Those are the kind of relationships we see a lot in physics, and so that's what we're going to see here as well when we go ahead and do this. So moving on, we should expect there to be some sort of constant. We have mu naught, which is a constant of proportionality for magnetic fields and how they behave in vacuums. Right? This is obviously not a vacuum, but you get the basic idea. It's also perpendicular because it's a cross product to both I and R. So that's helpful. And this is the equation that's on your equation sheet. Biot of R, you integrate mu naught over 4 pi, which is the constants, the current I times dL crossed with the R. That R hat is the unit vector R, so it has no length because we're dividing by 1 over r squared. So that's the basic idea. Does it make sense? Hopefully a little bit. You will actually use it in this form. You will take this, and the angle is the angle between dL and r, which usually we will try to get that angle to be 90 degrees in many of these examples that we actually care about. And that's the thing. We don't want to try to overcomplicate things as much as possible. Right, we want to keep them as simple as we can. And so that's what we're really looking at here. The units are Tesla, and that's where they all come from. I'm sorry, page 6 is incorrect. That is incorrect. Let me pause. If we're looking on packet page 8 and 9, there's some examples of this that I'm going to go through. You don't, again, have to do all of these, but I wanted to go through them so that you had the information for you. So if we start with a ring of charge, we're going to look for the magnetic field at the center, ring of current going around in a spiral. What is the magnetic field at the center. Now, the first thing to do is realize that regardless of where you grab the circle of wire, your fingers are always going to be pointing into the screen or into the page in the center of the circle, which means that we don't have to worry about different pieces of the magnetic field going in different directions, so we don't have to worry about adding a special trig function. Mu naught over 4 pi is a constant, I is a constant, and the sine of theta is going to be a constant, which is because the current is always going to be perpendicular to the r vector, always pointing inward or outward, depending on how you think about it. So theta is 90 degrees. And so we really simplify this down. R is also going to be a constant, so that can be pulled out of the equation. So we end up with mu naught over 4 pi, I over r squared, integral of dl, just the circumference of the circle, which is 2 pi r. And we end up with this interesting result, mu naught I over 2r. So the bigger the current, the bigger the magnetic field, and the bigger the radius, the weaker magnetic field, which hopefully makes sense, right? You're further and further away from that current, so you get a weaker magnetic field. We can plug in some numbers here. We had an example, so we get about 2.5 times 10 to the negative 5th Tesla into the page. And that's how that one works. If we go on to the next one, here we have a slightly more complicated situation. We have two sort of straight segments and then two half circles. The reality here is that it only looks a lot more complicated. We have to be a little bit careful, but we can solve this one pretty easily. There's a bunch of vectors here, but we really would prefer just to be adding up scalars. So let's think about what's happening. We're going to add up the vectors at point P that are the magnetic field from each of the little segments. And so let's treat them one at a time. A, B, and C, D are going to do nothing because the magnetic field curls around the wire. It doesn't go out that way, so it's going to have no effect on point P. So now we're left with the section B to C, which is a curve kind of going clockwise with the current, and D to A, where the current is going counterclockwise. Well, the outside loop is going to make current come around counterclockwise, so the magnetic field will be coming out at us. BC, it's going clockwise, so the current will be going into the page. And so if we put those two things together, we can say that we're really just subtracting the magnetic field from each of those effects. We're also going to look at this, again, because we've put this at the center, and R is always going to be perpendicular to the current. We can nicely use 90 degrees, so it's perpendicular. And we can write these out as the into the page minus the out of the page. We could do them in opposite directions. It doesn't matter, but that's the key thing. In this case, the negative is the out of the page. So if we end up with a negative number, we know that the out of the page is bigger. If we end up with a positive number, we know that into the page is bigger. And you can probably, well, you may or may not be able to guess just from this what it's going to be. But here we have the R is, the distance we are from a half circle. That's where we've got this equation. If I highlight this, right, we've got here the 2 factor is basically we've got 2 pi r, and then we've times all of the constants divided by 2, right? The 2 is the thing that we're getting rid of because we're only using half circle there, which is kind of an interesting result. So, oops, clear, switch out of pen. There we go. We get a lot of things that cancel out nicely, and we simplify down into this final result, which is that mu naught I over 6a into the page. So again, it's a relatively simple answer. We could go ahead and plug in the numbers that they gave us and find that if we wanted to. If we do a ring but not in the center of it, the geometry of this one is actually a little bit tricky. If you think of what's happening here, there is the distance r, and the curve, if you grab the part going in, it's actually out at the far edge. So the magnetic field is kind of pointing down and to the left. If we go to the bottom, we've got up and to the left. So what we really need to do is eliminate anything up or down and go with only stuff that is in the direction we care about, which is in or to the left in this case, which again, we've done problems like this. We have to be careful about the geometry, and we have been before. So the dB sort of form like a little cone, and the net magnetic field is to the left. So we're going to try to find the trig function that will give us just the part we want. So notice I've added a new angle here, not theta, so we're not confusing. We're using phi. But basically, we're going to multiply each little dB by the sine of phi, and that angle actually is a constant because the shape of the cone is consistent all the way through, which is nice. And so we're going to use that piece to make an argument about what should go there. Now, the sine of phi is basically r, capital R, the radius of my ring, divided by little r, which is the hypotenuse of that triangle. And of course, little r is also something we can kind of eliminate. Those two angles are not the same. What is theta? Well, theta is 90 degrees, again, which is nice. So if we put everything together, we know that that sine of phi is big R over little r. And we plug everything in, and we end up with that result. Plug in our numbers, and we get 2.25 microtesla to the left. Right. So there's a lot going on here, but the big idea is that we actually want to use this technique for a couple of simple answers. And if you look at pages 8 and 9, you can see kind of all those different examples. But for a long straight wire, which is our most common thing, or for a ring, those are the ones we want to use because they're the ones that are the most helpful. There's also some other resources you can look at about Biot if you want to. There's a couple of Mechanical Universe videos that are interesting to watch if you want more information. But we're going to use a slightly easier technique called Ampere's law next to make this a simpler task.